Okay, so let's finish up with practice problem number 2 for Unit 8, Lesson 6. So two treatments, A and B, are showed promise for treating a potentially fatal disease. A randomized experiment was conducted to determine whether there is significant difference in the survival rate between patients who receive treatment A and those who receive treatment B. Of 154 patients who received treatment A, 38 survived for at least 15 years, while 16 of the 164 patients who received treatment B survived at least 15 years. Treatment A, or Part A says treatment A can be administered only as a pill, and treatment B can be administered only as an injection. Can this randomized experiment be performed as a double-blind experiment? Or why not? So remember that double-blind experiment means that both the patient and the doctor does not know what is given. But since the treatment can only be given, treatment A can only be a pill and treatment B can only be an injection, people are going to know what they're taking, right? They're either going to be taking a pill or they're either going to be taking an injection. So this experiment cannot be a double-blind experiment. This is because people will know which treatment they are getting, since treatment A can only be a pill and treatment B can only be an injection. The conditions for inferences have been met. Construct and interpret a 95% confidence interval for the difference between proportions of population who would survive at least 15 years if given treatment A and the proportion of the population who would survive at least 15 years if given treatment B. So this is a two-prop confidence interval. P1 is the true proportion of patients given treatment B or treatment A who survived 15 plus years. P2 is the true proportion of patients given treatment B who survived 15 plus years. So let's go ahead and do the math. Well, first we need to find what P1 and P2 are. So P1, representing treatment A, had 38 out of the 154 who survived 15 plus years, so that's 0.25. P hat 2 is for treatment B. That's 16 over 164, which is equal to 0.098. So, which is approximately 0.1. So we have P hat 1 minus P hat 2 plus or minus Z star times the standard deviation. So plus p hat 1 minus p hat 1 over n1 plus p hat 2, 1 minus p hat 2 over n2. So that's 0.25 minus 0.10 plus or minus 1.96 times the square root of 0.25 times 0.75 over 154 plus 0.10 times 0.9 over 164. And we get our interval to be 0.067, comma 0.231. We are 95% confident that the difference in proportion of patients who survived 15 plus years is between 0.067, comma 0.231. In many of these types of studies, physicians are interested in the ratio of survival probabilities, PA over PB, where PA represents the true 15-year survival rate for all patients who receive treatment A, and PB represents the true 15-year survival rate for all patients who receive treatment B. This ratio is referred to as the relative risk of two treatments. For example, a relative risk of 1 indicates that the survival rates for patients receiving the two treatments are equal. So if we do PA over PB and it equals to 1, that means that they have the same survival rate. Whereas a relative risk of 1.5 indicated that the survival risk of patients receiving A is 50% higher than survival rate for patients receiving B. An estimator of the relative risk is the ratio of estimate probabilities P hat over A times P hat over B. Use the data from the randomized experiment described above, compute the estimate of relative risk. So what this is saying is P hat A divided by P hat B, which is equal to 0.25 over 0.10 is equal to 2.5. Sampling distribution of P hat A is skewed. However, when both sample size A and B are relatively large, the distribution ln of P hat A over P hat B, the natural log of the relative risk, is approximately normal with mean of P hat A over P hat B and a standard deviation given as this, where PA and PB can be estimated using P hat A and P hat B. When a 95% confidence interval for ln of PA over PB is known, an approximately 95% confidence interval for PA over PB, the relative risk of the two treatments, can be constructed by applying the inverse of natural log to the endpoints of the confidence interval. An inverse of natural log means we're doing e to the power of x. So the conditions of inferences are met for the data in the experiment above, and a 95% confidence interval of ln of PA over PB is the interval 0.3868, 1.4690. Construct and interpret a 95% confidence interval for the relative risk PA over PB for the two treatments. Well, what it's trying to say is that ln of PA over PB is given by this interval. Now, to get rid of the ln, I need to take e to both sides. So I have to do e of 0.3868, comma e to the 1.4690. And this gives me an interval of 1.47, comma 4.34. This means that we are 95% confident the relative risk is in the interval of 1.47, 4.34. What is the advantage of using the interval in part D over the interval of part B? Well, remember that we want our relative risk to be higher, right? We want it to be as big as possible. In part D, we get an interval much bigger than 1, which shows that treatment A works a lot better than treatment B.